equal to the net force. You then divide that by the mass and you will get the acceleration. That is the idea. That is the whole idea in a nutshell. If you've learned that, you've really learned everything. Although, as you might suspect, some of these problems can have a lot of details to them. So the real key is paying attention to the details. Which forces are present, which ones are not. Which ones are acting on the object, and which ones are acting on other objects. We often call it the surroundings. And so that's kind of the tricky part here, especially when we get into a lot of forces. So, as you recall, we did one example when we left on Monday, and so I just want to pick up and do example after example after example after example. And if we're fortunate enough, we will finish my list of examples, and we will go into Chapter 6. In Chapter 6, I'll just say, let's just do more examples. Because in all the examples I do here in Chapter 5, you will see that things are going to either go fast, or they're going to go slow, or they're going to, not accelerate at all. But there won't be anything turning. But that's what the next chapter is about. So keep that in mind, that Chapters 5 and Chapter 6 are really the same thing, using Newton's laws of motion. And so we start with the easy ones, if you want to call them easy here in Chapter 5, and I hope you do. Based on your test scores from the first one, hey, you guys all know this, and so you're more than ready to go into Chapter 5. So good. We'll jump in here into Chapter 5. So that is the summary of this chapter. And in fact, I thought I would begin by saying, and don't forget this. That was your question. Watch what happens next. If you know the acceleration, what could you find? Velocity. And if you know the velocity, what could you find? Position. So that's the chapters 1 through 4. If I was kind of summarizing what we've done this semester, I would say, okay, there is our chapters 1 through 4. We started off with Chapter 1, scientific notation, unit conversion. We went into Chapter 2, and what is speed, velocity, and acceleration, and how are all they related in terms of derivatives, and what if there's a constant acceleration. We then learned a little bit more math in Chapter 3. Chapter 4, we saw a two-dimensional motion. That's why we learned the math in Chapter 3. And so that's what we've done so far, is Chapters 1 through 4, where we learned what we call kinematics. We're now going into what we might call here dynamics. We look at their forces. We add them together. We find out what the acceleration is. And most of our problems will stop right here. Most of our problems will be the idea that you take the forces, you add them together, you get the acceleration. End of story, with the idea that you could go on. You haven't forgotten those, but once in a while the problem will ask, continue on down. Now that you know the acceleration, go to velocity, go to position. And so don't forget these in some of the problems that want you to put everything together, because that really is the ultimate story. It's not just one chapter at a time. I wish life was that simple and the science and the engineering was that simple. It's all of this going on at the same time. So we learn it piece by piece and try to put it all together when it's, applicable at the very end. Well, that's why I put an arrowhead. I didn't put equal to. So maybe I'll add that in there. I'll change colors. But you're right. To go from net force to acceleration, you divide by mass. And likewise, to go from acceleration to velocity, you integrate with respect to time. And to go from velocity to position, you integrate with respect to time. So that's how you get from one to another. But I think you already knew those, so I didn't put them in the little diagram. But the diagram kind of shows the overall approach. Look at the individual forces, add them together to get net force, divide that by its mass to get its acceleration, integrate that to get its velocity, integrate that to get its position. And so that's the semester so far. Obviously we're going to learn more before the semester's over, but that's what we've learned so far as we've done our kinematics and now into our dynamics. Well, as you know, we did that corny one with a bag of cement hanging from the ceiling, but it was a good one in the sense that it showed you about the tensions and free body diagrams and those 4 steps that I think are good to commit to memory. Number 1, you got a good physical picture of what's going on. Number 2, draw that free body diagram. Number 3, write out the equations that are associated with that free body diagram and Newton's second law. And then finally, number 4, solve it. Do the math and come up with the answer. And if you want to throw number 5 in there, go back and take that answer and substitute it back in to see if you did your math right. Of course, that's only checking to see if you did your math right. So if you had laid out your physics wrong to begin with, then you just have solved the wrong equations right. That doesn't help. But nonetheless, the last step of plugging it back in isn't such a bad option either there. But at least do those 4. Well, the second one on my list is number 40. It's kind of similar to number 20, slightly different here. Let me read it if you don't have it there in front of you here. But it says, a woman at the airport is towing her 20-kilogram suitcase at a constant speed by pulling on a strap at an angle theta above the horizontal. She pulls on the strap with a force of 35 newtons. The frictional force on the suitcase is 20 newtons. Okay? And then it goes A, B, C, or maybe just A and B. All right? So then there's 2 questions. But I'll pause there and turn around and start to draw a picture of it. Because this is our step 1. Step 1 is, do you got a good physical understanding? How about that? There's a strap at some angle theta. All right, that's the best I can do, I guess. All right, a little stick figure there. Okay, and so what this is, and let me just read it again. So we've got a woman at the airport towing her 20-kilogram bag. All right, so 20 kilograms. At a constant speed by pulling on a strap at an angle theta. So there's the strap, there's the angle theta, above the horizontal, all right? She pulls on the strap with a force of 35 newtons. So we don't know the angle, but we know the amount of force she's pulling on the strap. We also know the mass of the suitcase. The frictional force on the suitcase is 20 newtons. So as these wheels try to go and spin around here, there's some rubbing going on. And there's some friction going on. And they just tell us that number. It's 20. All right? So I'll stop there. You got a good physical picture of what's going on? And I'll say it again. It's that first step that really helps you from going down the wrong road. You just kind of lay it out. Okay, I know what it is. I know what where I want to go. And you won't go down a lot of mistakes by having a good physical picture. Number 2. What do I do next?
Free body diagram.
Good, free body diagram. So I'll just put free body diagram, F, B, and D. All right? So free body diagram. And what does that mean? Well, that means to help our thought process, don't think about anything else, just the object in question. So I'm going to draw the suitcase. I'm not going to draw the floor of the airport. I'm not going to draw the woman in the airport and anything else that might be in the airport, okay? Just the object. Now, draw all the forces on that object, okay? And this is where the physics becomes real important. If you miss any forces or create any new ones out of nothing, then when you write out the equations, obviously they're wrong here. So, look for everything touching the suitcase plus the force of gravity, okay? That's kind of the key here. All right, so what forces are here? Rattle them off. Tell me. Give me one. Okay, good. So I heard friction. That one I'll put here and label its number, 20. Okay, I heard somebody say the strap is being pulled, and we were told that that was 35. Okay, another one?
Gravity.
Okay, gravity. Now, when you say gravity, maybe we should say the force of gravity, because there's an acceleration due to the force of gravity. And so I don't want to say that the force down is 9.8, right? That's the acceleration under free fall and blah, 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 blah. But so this is the force of gravity. So the force of gravity, and then if you want just one word, say weight, don't say gravity. Okay, so weight. All right, how do I calculate that? Yeah, that's mg, and I do know that one. M was, or is, 20 kilograms, and g is the 9.8 meters per second. So 10 twice is 20. And I guess we're a little shy of that with no decimal. Yeah, so 196 newtons there. All right. So any other forces? Yeah, don't miss it. The ground is pushing up. That's the one we went through also. So this thing is on the ground pushing up. And we've been using the symbol N. Lowercase or uppercase? Yeah, I think he's been doing a lowercase there. Okay. Any others? Yeah, let's see. Woman's touching it. Got that one. Ground is touching it. And in that case, I got those. Right? There's the perpendicular one, which we call the normal, and then there's the one along the surface, which we call the friction. Okay, so then those are the only two things touching it. Then the force of gravity, which we call weight. End of story, right? So I got them all and didn't add any extras. Good. So there's the two big steps, if you will. There's the two physics steps. Good physical picture, free body diagram. Step 3, write out the equations. All right, so the equation says the sum of all the forces have to equal mass times acceleration. Now remember, that means two equations. That means all the forces in the x direction have to equal to mass times acceleration in the x direction. And it also means all the forces in the y direction equal mass times acceleration in the y direction. So don't forget our vectors, right? So we mean by this little arrowhead up there that there's I hats and j hats. So the i's go with the i's and the j's go with the j's. And if you want to write them, somebody said this last time, as one big equation with i's and j's on one side and i's and j's, that you're welcome to do that too. But I think at this first beginning level, it's kind of nice to just say, I'm going to write it as two equations. I'm going to put x's with x's and y's with y's, and I've got two equations simultaneously going on. Because if I do that and put this equation here and do that and do this equation here, let's see what I get. What are the forces in the x direction? Yeah, if you want to go around it, I heard somebody say, well, there's the frictional force. Good. And so that's a negative 20. Now I suppose even before I can say x and y direction, I should probably say, well, what coordinate system are you using? And I was just thinking the traditional standard one, and I don't see any reason of changing it. There will be times where I probably will feel like changing it, and I'll mention that. But in this case, I'm thinking the conventional one, so when somebody said minus 20, I agree. Yeah, this is a force, and it happens to be that way, which is the traditional negative direction. And so my first force in the x direction is a negative 20. How much of the normal force is in the x direction? None, right? That's all vertical direction. Okay. How much of this one is in the x direction? Good. So it is a 35 newtons and cosine of some unknown angle theta, and in the positive direction. So there's that magnitude component direction part of it. Okay? And then finishing with my last force, how much of the weight is in the x direction? None, right? So of those four forces, only two of them were really relevant for the x direction. And that has to equal to what? Okay, mass. Suitcase is 20 kilograms. Acceleration? Is that another unknown? Yeah, you caught it there, right? What did it say in there? Constant speed. A woman pulls the suitcase at a constant speed. What's the acceleration? 0. Okay. And so don't read these too quick. I mean, it's clearly right in there. It just is not going to say as simple as acceleration 0. That would be too easy. That's a physics 102. That's a, high school, middle school answer here. This is, hey, we pulled it at a constant speed. What does that interpret? What do those words mean? And so this would be equation number 1. Now you can see in that equation, there's only one unknown, the angle theta. And I suspect, even though I haven't even read the questions yet, that is one of the questions. I'll read it now. Question A. What angle does the strap make with the horizontal? There it is. 2. What is the normal force? All right, so those are my two questions. So I can answer this first one really easy with this. This would tell me, after a little bit of math, the angle. And so I would have cosine theta equals, and if I move this over to here, I've got a 20 in the top, and then divide by the 35, and get out my calculator. I can then find the value of that angle. So Oh, I better check the mode on this because, good. I was using radians last night. Okay, but back to degrees here. Okay, so let's get the angle. And I guess I could get the angle in radians, but I think you'll feel better if I do degrees here. Kind of a judgment call. But in this case, I like degrees here. So I'm going to leave my calculator in degrees mode there and say, okay, so the angle is 55. So we've got an angle of 55 degrees. Okay? The same thing in the y direction also, and you can see that the y direction is going to have the unknown n, and that's the other question here. So let's write out the forces in the y direction. And I'll go through the same order here. I'll start where you started before. How much of the frictional force is in the y direction? None. How much of the normal force is in the y direction? Yeah, all of it. So I'll just say plus n for the first one. How much of the normal force, I'm sorry, how much of the force from the woman is in the vertical direction?
35 sine.
Yeah, so there's the magnitude. There is the component. And there is the direction. So magnitude, component, direction. Okay, that's how much is in the vertical direction. So we've got a part there. Then notice I put the angle in that I just calculated from it. So I put in the 55 degrees. I know. Keep going around. How much of the weight is in the vertical direction? Yeah, all of it, and it's all down. So I'll put a negative 196. Right? Newtons, if you will. And did I finish? Yeah, so that was all four. So as we look around at all four, only 3 of them have something in the vertical direction. And that has to equal what? Yeah, mass of 20. Acceleration? Y 0.
No acceleration in the y-axis.
Okay, I just want you to be careful. You're saying it right here. But it's not because it's moving horizontally at a constant speed. That tells you it has 0 acceleration in the x direction. What tells me it has 0 acceleration in the y direction? Yeah, it has 0 speed in the y direction, and it's not changing its speed. So it has a 0 speed in the y direction. It remains a 0 speed in the y direction. So the same idea. There's no change in speed in the y direction. It starts at 0. It's always at 0, even though the x does have a speed. Okay, so careful with that we keep the x and y components separate. That's why I was saying chapter 4. You need to keep that picture in your mind. You know, you need chapter 4 to work in chapter 5. Yeah. Oh yeah, so it could have been falling, you know, so maybe somebody, you know, pulled it off the top level. You know, she's in the transportation bus and it's up here. And now as she's pulling it this way, it's also falling that way. So it has a horizontal acceleration and a vertical acceleration. So there's a lot of different cases, which, of course, I'll use this as a great opportunity to say, I mean, what are we trying to get accomplished here? What's this whole class about? What is physics about? Physics is knowing how to apply a few powerful fundamental concepts to explain a universal phenomenon. So there's tens of thousands, if not hundreds of thousands, if not millions of problems that we can set up because of this. And we have all the answers right here. That's it. And so the best I can do is just show you a handful of examples. Let you do a handful of examples, and the idea is now you can do any of those millions of problems. And so when you see one of those millions on the test, you'll be able to do it. That's the idea. Yeah. 9.8 is what you get when you just drop it, right? And it's not falling, it's rolling across. And the 9.8 is certainly what I would have got if I didn't have a normal force. So if there was no floor here, it would have fallen down, right? Well, and I guess fell without the woman holding it or the normal force. We got to get rid of both of those. And then we would lose our friction, and then we're just back to free fall, and then we're back to problems we've already done. So our problems are now more sophisticated than that. Our problems are not just the force of gravity.
If she was rolling down a ramp, you would have all the...
Oh, rolling down a ramp. I'm glad you asked. Maybe we should do that next. So that's coming up, definitely, yeah. So we'll go down a ramp next. But just building up here one step at a time, this is how this one would work out. And so again, you can see that the only unknown here is n. So now we can go to our last step, step 4, solve the equation. All right, and so n equals, and so as I move this over to here, it's 196 minus 35 sine of 55 degrees. And so there's going to be the normal force. Okay, and so 196 minus 35 times sine of 55, coming up with 167 newtons. And so I've answered their two questions. I'm going to throw a C in here. I know it's not listed here. Yeah.
Oh, no, newtons. You put it in newtons.
Yeah, and again, this is newtons, that's a newton, that's a newton, that's a newton, so that's a newton. Yeah. Yeah. So. But let me throw in a question C, and the question C is probably not, and I understand why your author didn't put it in, because if you've ever seen or used a suitcase, they're often on wheels. Fair enough? But let's pretend that we don't have wheels. Okay? Now, I know you really wouldn't want a suitcase like this, okay? But we haven't talked about wheels and rolling, but solid-to-solid sliding, have we talked about that? Yeah, we talked about the friction there. Okay, so let's just pretend, slightly different than reality here. This is a suitcase without wheels and you're pulling it across the airport floor. What kind of friction would it be? How would you classify this? Yeah, I would call it kinetic. You're right. Why? There's sliding going on. There's motion between it. When would it be static? Oh, now be careful with the phrase no motion, but when there's no sliding going on, right? Now, I only say that because what if it was a little different here? What if we weren't talking about the suitcase sliding across the floor? What if we were talking about the shoes as we walk across the floor? What kind of friction do I have there? Isn't that static? Why? Because there's no sliding between my foot and the floor, right? But am I moving? Yeah, so be careful with that phrase that, hey, I will use static friction when it's not moving. Oh, no, 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 no. Let's look at a car. You got a car with wheels, with tires, rolling down the road in a normal situation, so you're not locking up the brakes and skidding. But in a normal situation, rolling down the street, what kind of friction would we be talking about?
Static.
Static? Mm-hmm. Static. Is the car moving? Yes. But where you got a static friction involved because there's no sliding between the tires and the road. Now, if something runs out in front of you, you slam on the brakes, you know, and so comes a cat and you go, oh no, and you slam on the, or maybe you'd step on the gas with a cat. A dog, and if a dog goes, you slam on the brakes here, and if you put on the brakes here, the wheels lock up, right? And then what friction do you have? Then it's kinetic, right? So I thought I would use this as an opportunity to say, all right, so don't miss those different frictions. And that's all we've talked about so far. We've only talked about when you have a solid sliding on a solid and when a solid is not sliding. We haven't even done the wheels rolling yet, so that's why I had to throw away the wheels. We will. We will soon, but not yet. And we haven't even done any air resistance yet. And we will, but we will. That's in the next chapter too, coming up. So all that is building up. I only say that then because what if the question went to part C and said, what's the coefficient of kinetic friction? So kinetic friction was this coefficient times the normal. Do you remember that one? Okay, and so what this is saying is how much friction do you get depends on two factors. This is the material. Kind of makes sense, kind of how rough it is, what kind of material you have. So that would depend on what is sliding here. We don't know, so we're just going to find a number. But this could be, I mean, if it's an airport, it could probably be tile or carpet. That's usually what you find in an airport, all right? And the suitcase, vinyl or canvas or something like that. But anyways, there is an interaction there of what those materials are made of. And that's what this coefficient is. What's the N though? Okay, it's the normal force. And why is that in there? Because that's the force between the two. And you could imagine that if the normal force was more, if there was more interaction, wouldn't you expect more friction? And less interaction with less friction? Yeah, exactly. And so we see those two factors here. So just to throw in a part C and give me a chance to mention friction here, the problem could have gone on to say, what is the coefficient of kinetic friction? And to do that, you would need to know the friction, which they gave you, and the normal force, which you just solved for. So in this case, the friction is a relatively small number, 20, compared to the normal force at 167. And so we can then figure out what the coefficient is for this. And so 20 divided by 167 is about a 0.12. And so there would be the coefficient of friction. And the units, I guess, would be Newton divided by Newton. So no units. That's why it's called a coefficient. It has no units. It is just a ratio of two forces. And you just end up with a number. Shall we try the down the hill one? You got it? All right. So if you're good with that one, let me try another one. And hopefully, before today's over, you will be in a good spot to see the pattern, and that you can go home and, particularly this weekend, work on these and say, all right, I got the idea. Physical picture, free body diagram, write out the equations, solve the equations. And then you just got to look at what's going on. And some of these can be simple, and of course so far we started with the simpler ones, and then they can get harder and harder and harder. So I'm just going to continue to do more examples. Here's one on a hill, 24. It's got an object on a hill, on an incline. It says here, draw the free diagram for a block that slides down a frictionless. So we're not worried about the friction here. I'm worried about how you're going to handle when something's on a hill. What's going to be different about it? So that's why I picked this one. But you're going to put a block on a frictionless plane that is inclined at 15 degrees. The block will then start at the top, and the length of the incline is 2 meters. A, find the acceleration of the block, and B, find its speed at the bottom of the incline. Okay, so the block is sitting on an incline that they say is angled up at 15 degrees. Okay? Maybe I'll just put theta here to kind of, give you the abstract idea, because when you do them, it won't be 15 degrees. It'll be 25. But can you do it at 25 if I do it at 15? Yeah. So there's the angle. The block is sitting up here, something like that. They say that it starts from rest, and it will begin then to move down the incline. Kind of what you would expect if there's no friction there, right? If there was some friction, it may stay there, but without any friction, it's going to start sliding down. It's going to go faster and faster. It's going to accelerate. So that's one of the questions. What is the acceleration? Then it even goes further than that and says, well, what's the speed at the bottom of the hill? Well, I'll worry about that next, but let's just do the friction. All right, but I'll stop there. Good physical picture of what's going on, right? Box on a hill. No friction involved for this one. Just a little incline theta. How are you going to handle it? That's the point of this problem. All right, 2, free body diagram. All right, so let's get rid of the incline. Let's just draw the block. So there's the block all by itself. What are the forces on it? Okay, we've got force of gravity. What direction is that? Has it changed? No. Force of gravity is still straight down, so there's our mg. Any other forces? Yeah, anything touching this block? The incline is, right? So the incline, which way is it going to push? Doesn't the incline push perpendicular to the surface? Isn't that the whole point? And that's why I want to make sure you saw this, because you're going to see this a lot, and it's very helpful to see it the first time. But you need to put the normal force, as the name implies, normal to the surface. Now, could you have a force that is tangential to the surface? Yeah, what do we call that? Friction. Do we have it in this problem? No. So they're trying to say that, you know, yeah, you could add that, and we will at times. But for this one, no sideways force. So we have just the normal force. And it's because of that we'll begin to see why this thing goes down the hill. Okay? And so if you want to make sure you understand why it's going to go down the hill, I think you believe me, it will go down the hill. You've seen things go down the hill. Why do they go down the hill? Gravity's still pulling it straight down. But this free body diagram will hopefully show that. Any other forces here? Okay, I would agree it's moving, but is that a force?
There's no friction, so there's
Right, there is no other forces. So I'll say it again. Make sure you see all the forces and don't make any up. Okay, which is easy to do as a beginning student here. You just got to look for things that are contact. What's in contact with this block? Just that incline. That's it. So we can draw normal force, and if there was friction, friction. That's all we're going to get. And of course, the one not touching it is the weight of it. But that's it. So that's our free body diagram. Don't throw anything more in there. All right? Those forces, those two, combine together to tell me the motion of what is going on. And that's the question. I claim from that I can get the acceleration. And notice I don't even know the mass of the block. And the question says, what's the acceleration? And you're going to get it. All right? So, we're good with step 2? Free body diagram? All right, so we got a good physical picture, got a free body diagram. Step 3, write out the equations. Now, write out the equation means what's your coordinate system too, right? What are the x and y's? Do you want to stick to the traditional one? Or do you want to change it? Let me come over here for a second. What if I did change it? I mean, here's the block, okay? I think it's fair to say it's going to be going like that. Fair enough? And if you use the traditional coordinate system, x and y, not that this would be wrong, but if you stick to the traditional one here, what would you say about the motion on this block? Yeah, you would say it has an acceleration x and an acceleration y. Fair enough? But what if I were to change my coordinate system? That it's almost like the traditional, just a slight change, where it's now rotated a little bit. So instead of the x-axis being horizontal, it's kind of pointing down the incline. Now, which way does the box move? Just the x-axis. So will you have an acceleration in the x direction? Yeah. Will you have one in the y direction? No. And isn't it really nice when one of the equations at least is equal to 0? And I claim that's the way to handle a problem like this. Not all the time. You'll have to see what the advantage is. But I would say what's really nice about this is that the acceleration in the x direction is the total acceleration, and the acceleration in the y direction is 0. But over here, the acceleration in the x direction would be the total acceleration times cosine of some angle, and the acceleration in the y direction would be the total acceleration times the sine of that angle. So not only do I have the advantage of one of them is 0, but I have the other advantage that I don't have to worry about sines and cosines of some angle. And so this tilted axis is why I picked this problem. Use a tilted axis for this. Here's my clue for you. Since you are going to be setting up in equations and set it equal to ma, if you set up one of your axes in the direction of the acceleration, that means the other one will be 0. That's the key to remember. If you can. I'm not saying every problem can be set that way. And I'll even put a disclaimer that maybe some problems are better not to. But for the most part, I would say that if you set up an axis, and you're going to really see this in the next chapter 6, I'm going to say set up your axis so that your x-axis is in the direction it accelerates. Because once you do that, your acceleration in the y direction goes to 0, and you don't have a harder math problem that has sines and cosines. Fair enough? That's really the lesson of this problem. And so that's what I would like to do here. Let's set it up so that when I take my coordinate system, my coordinate system is down the incline. Okay? So I'll say it again. Do you see that advantage? Do you see how this now becomes that? Because I need to point out there's also a price to pay. And the price to pay isn't so bad, so that's why I still think that is worth tilting our axis. But what do you notice about the force of gravity? It's not on the x and y axis anymore. So we can't just say the force of gravity is in the y direction. Right? Because the force of gravity is still going to be down. You tilt your axis, now it is not along the x or y axis.
The cosine of that theta, some theta wouldn't be 15?
Oh, yes it will be. So we need to talk about that angle. And so I'm glad you noticed it's 15. I haven't gotten that far, but yes, that's what it's going to be. Okay. So that's the price you pay. However, I think we've also gained a price, or gained something else here. Look at the normal force. If you hadn't have tilted your axis, wouldn't the normal force have x and y components? And now that you've tilted it, what happens to the normal force? Only y, no x. So we've gained something here, and we've certainly gained a lot in the acceleration, and we lost a little here. But overall, I think there's a net advantage, and I would encourage you to, I'll say it again, in this case, tilt your axis, but the general principle is set an axis in the direction of the acceleration, whatever that is. Because there's going to be some other problems where it won't be just down the hill, it'll be more complicated. And we won't want to go down the hill. In fact, in the next chapter, there's a good problem where the acceleration is not down the hill, but students still want to put it down the hill, and they make the problem harder on themselves. So remember, I'm not saying down the hill. I'm saying point it in the direction of the acceleration, which, in this case, is down the hill. All right? That's the advantage. All right, so on further to step 3. So step 1, got a good physical picture of what's going on? Good. Step 2, got the free body diagram? Good. Step 3, write out the equations. And like I said, writing out the equation is first getting a coordinate system. So then I can say, let's look at the sum of the forces in the x direction, setting that equal to mass times acceleration. And let's also look at the sum of the forces in the y direction. Just remember, we've got a tilted axis. All right, so I'll start with this equation. What are the forces in the x direction? There's only 2 of them. There's a normal force. How much of the normal is in the x direction? None. Okay. How much of the gravitational force is in the x direction? Okay, so it does have some, and that's why it goes down the hill. Right? There is a component of it. And so maybe we should draw the components. I'll change colors into red here. But if you are looking at a vector that points down like this, you can think of that one as being so much along the y-axis plus so much along the x-axis, right? And so these two added together is that one. So this is the part that is down the hill. And if I call this angle theta, then the part down the hill would be magnitude times the sine of theta down the hill. Magnitude, component, direction. So that's why I picked this one. So you can see there, viewing it this way, I've got a component down there. And now I can answer yours, which, wait a minute, don't I know that angle theta? Because wouldn't that angle theta be somehow connected to how much I tilt my axis? And how much I tilt my axis, isn't that related to this whole incline to begin with? And so maybe if you put your axis back here in this picture, it was straight down and straight across like that. The whole reason you tilted it so it would be parallel is the reason you tilted it 15 degrees. You see that? And so if you tilted it 15 degrees, isn't that 15 degrees? I mean, you just imagine these two sticks and you just grab them and you're rotating it 15 degrees. So that angle is 15 degrees. So this angle is not just some unknown angle, theta, but for this one, it's 15 degrees. Another problem, it may be 30 degrees. All depends on the incline here. But I know that. So this is equal to 15 degrees. Right? Maybe I'll just write it right below here. mg sine of 15 degrees. Any other forces in the x direction? No. You already said the normal force didn't have one, and then that's the gravitational force. Does it have a component in the x direction? Yeah. What does it have to equal? Mass times acceleration. Now you can call it acceleration in the x direction if you want, but that was the whole nice thing of tilting our axis. The acceleration in the x direction is the total acceleration. So call it an x if you want. You don't need to. And then we'll notice what happens. Mass cancels off. So they didn't give it to me. Just as well, I don't need it. Right? So the acceleration, acceleration is 9.8 meters per second squared times 15 degrees. That's what that first equation gives me. And so I can answer that first part. A, what is the acceleration down the hill? 2.54? All right. So 2.54 meters per second squared down the hill. There it is. And so that's how we would apply Newton's second law to this problem as it is down the hill. Okay? And there's those 4 steps, right? Good physical picture of what's going on. Draw the free body diagram. Write out the equation or equations for the free body diagram, and then solve it. And I've done it. Right? Now this problem goes a step further. This is really the main point of this chapter, is to get you to figure out what the acceleration is from the forces. But if we know acceleration, couldn't we get velocity and position? And this one does say what is its velocity when it gets down a position of 2 meters. So we'll go one step further, but this is old stuff. How am I going to get the velocity at the bottom of the hill? Well, let me ask you, does it have a constant acceleration? Yeah, it does, right? I got a number, 2.54. Does it change? No, and you can see here that the acceleration then has to do with the slope of the hill, right? And so if this was a hill that changed its slope, then I would say its acceleration is changing as it goes down. Be a harder problem. We'll wait for chapter 7 and 8 for those. But for this one, all the way down the hill has the same angle. So that's the acceleration it has at the beginning, at the middle, at the end, all the way down. So does it have constant acceleration? Yes. So could I use those constant acceleration equations? Yes. And so the one that pops into my head is number 3, which relates velocity, acceleration, and distance. I'll plug those in, but it looks like you have a question back here. Yeah,
I was wondering, you know how it's 15 degrees?
Yeah.
To find the force in the x direction?
Yeah.
Could you subtract 90 from 15 and get 75? And then put cosine of 75?
Yeah. Oh, absolutely. Yeah, absolutely. Because, sine of 15 degrees is the same as cosine of 75. And so your focus is on this angle, 75, and then you want the adjacent piece of it. So yeah, certainly. Yeah, no problem. And so now, if I put in the numbers given, they say start from rest, okay, have an acceleration of, so that's the 2.54 I just did, and go for a distance of 2 meters. So if I put those in my calculator and take the square root, what do I get? So 2 times 2.54 times 2 again equals square root of all of that, and is about a 3.19. So 3.19 meters per second is the speed of this one at the bottom of the hill. And so this is a good example where they said, look, use Newton's laws that we just learned here in chapter 5 and 6, and then use that with our old stuff to figure out what is its speed at the bottom of the hill. Now, I'm really done with the problem. They haven't asked a single thing about the y direction, but for completeness, shall we do the y direction also? All right, let's write out that one, okay?
They only ask for acceleration and velocity?
Yeah, they only ask for acceleration and velocity. So it turns out I don't even have to do anything in the y direction. So if this was a homework problem or a test problem, move on to the next one. We're done. But in terms of education, maybe I should look at that one too and say, okay, what information is there? All right, let's look at the forces in the y direction. So I'll start again. Let's come over to the first force. How much of the normal force is in the y direction? All of it, right? So I will put an n. It's in the positive direction. So there's my first force. How much of the gravitational force is in the y direction? Good. You saw it, right? It is magnitude mg. The component would be cosine of 15 degrees. What direction? Negative, right? So there's the magnitude component direction. So that's how much of the gravitational force is in the y direction. That is the normal force. What does it have to equal? 0, right? That was the whole discussion about why to tilt our axis. Because once it tilts, it has an acceleration only in the x, nothing in the y. And so we could now say the normal force is mg cosine of 15 degrees. Now they didn't give me the mass, but if they'd give me the mass, now I can get my calculator out and find out what the normal force is, right? And if there had been some friction, we didn't even know the normal force to get the coefficient of friction, right? Now they didn't ask any of all that, so I'll move on to another problem where they do ask it. But I wanted to show you that this is why we might care about the y direction here to figure out what the normal force is. By the way, in passing here, did you notice that the normal force does not equal the weight? And there's I think a human tendency, and I see it again and again on the next test that's coming up, but it won't happen this semester, right? Nobody will just assume the normal force is equal to the weight. Okay, but it doesn't. You got to work it out. Does it equal the weight sometimes? Oh, sure. If it were weighted all the time, I'd just tell you that, and then it would be a lot easier problem. But it's not. You got to write out the equation for that specific problem. And so, noticing here it doesn't equal to the weight. Remember the suitcase? How much did the suitcase weigh? 196, right? What was the normal force? 167. Is the normal force equal to the weight of the suitcase? No. Okay. So here is two good examples where the normal force doesn't equal the weight. And there'll be some other examples where it does. But so don't just be doing the homework of the test and think, oh, normal force. Write it out. Write out the equation. I can't make it any simpler than that. Write out the equations. See what it gets. You got to work it out. Yeah.
Would it be the surface that would change that, or?
No, in the case of, say, the suitcase, we had this. We had the weight pulling it down, but we had the normal force pulling up, and we had a component of the woman pulling it up. And so all the ups have to equal all the downs. If the woman wasn't pulling on it, that would be a good case where the normal force equals the weight, because all the ups have to equal all the downs to get zero acceleration.
Or if she was pulling directly across with no up.
Okay, fair enough, yeah. If she was pulling directly across, then the up would equal the down. But once she starts pulling up or pulling down, since all my ups have to equal all my downs, these two can't be equal anymore. There's something else into play here. Or for that matter, if it was accelerating one way or the other, then these wouldn't be equal either without the other force, right? We have to have one bigger than the other to get the acceleration. So there are many cases where the normal force is not going to be equal to its weight. There are many cases where it does, and we will do many of those examples. But this first one is one that I wanted to point out. It does not. So careful with those. All right. So far, so good? All right. Shall we try more? And what I want to, of course, get across is that are you beginning to see it's just the same thing? You're just doing the same thing again and again. And I don't want to bore you, but really, if I can get to a point where you're bored, we're there. You're saying, this is the same thing. Come on, you're just writing out Newton's second law and solving it. How many times I got to see this? Let's move on. And when you see that, you see the basic principle of the physics. Newton's laws of motion, a few simple principles explain all the motion, right? Explain the universal phenomena. And so that's where we're headed. So let's try this one. It is a little more complicated because we've got two objects here. This one says, in number 26, we have a 5 kilogram object is placed on a frictionless horizontal table, which is connected by a string that passes over a pulley and then is fastened to a weight that is 9 kilograms as shown in the drawing. So maybe I'll do the drawing here. Oh, that reminds me of something here. Let me do the drawing and then point out something very important that's not related to the class, but almost as important as my class, which is your life, but not quite as important as my class.
It's not that important.
Nah. No, but I got to thinking about this, and I've seen, unfortunately, year after year, students don't see our scholarship foundation. We are fortunate at this community college to have one of the largest scholarship foundations. We've got some great, great scholarships. And this is the time you apply, and the closing date is this Friday. And I saw an email and I said, oh, crap. I should tell my students. I bet a lot of them have not even checked or scanned the book to see which ones they qualify for. Yeah. Oh, they extended it? Oh, good, good, good. So, okay. So the little booklet says March 2nd, but nonetheless, I'd encourage you before that. And I go, you know, I'm just going to print a bunch of these up. So grab one of these, okay? And if you are all interested in some money, look at this little booklet, okay? Sometime soon before the closing date. There are a bunch of scholarships. And there's one in particular I want to point out that gets overlooked all these past years. Yeah.
They make it really easy for you when you're applying. They also just, once you put all your information, it's just easy to just put all the ones that are for you and then you just apply quickly.
Right.
Apply and it's apply.
Right, yeah.
Can I help with this semester or only next?
I think it's starting in fall. And some of them are if you're here, some of them are if you transfer. It's a little early for you guys who are transferring, but there's probably some of you here or who are going to be at other schools. And so look at them closely. If you turn it to the back, I copied just a couple of them, but the first part of it gives you the website of where to go to. So I want to make sure you had that. And so I'd encourage you, go to the website. And when you get there, it will be this little PDF file that's got this little booklet. And they just list the scholarships. And they break them down by discipline. And I think that's part of the problem because this scholarship below it, the Laurie Converse Scholarship, it's the Converse shoe company and whatever else they make, right? It's listed way at the bottom under cross disciplines. And most of my students miss it, and I think it's the best scholarship out there for you guys. And so, unfortunately, in the past, we've had less people apply than the number of scholarships awarded. I mean, look at this. How many scholarships? 24. How much money? $2,500. So it is one of our biggest scholarships, and the most are given. So now look at the fields of discipline. It goes on to computer science and physics and mathematics and engineering and electronic networking and blah, blah, blah. So that, does it say preference?
It goes to men and women. It just says preferred.
Okay, but so women, all the more so. There probably won't even be 24 women who apply. You're a shoe in there, right? But in the past, I kid you not. Now, it hasn't been true recently because I told myself the last couple of years, I'm going to tell my students, I'm going to print it up, I'm going to put it in their hot little hand, I'm going to get people to apply. But before I started doing this a couple of years ago, I kid you not, I would, I'd get a call from the Scholarship Foundation, and they would say, you want to review these scholarships? And I'd go, well, how many are you awarding? Oh, 24. How many applied? 20. Well, that's an easy answer. You got only 20 people applied, there's 24, give them all the scholarship. And, and like I said, anyways, and then a couple of years of this went on, and so they said, well, they called me and said, well, how can we get more people to apply? I mean, what are we missing here? And anyways, after talking to a few students, I realized it wasn't that people weren't interested in the money, and it wasn't that they didn't qualify, it's just they kept missing it on the scholarship. It was way down under the cross disciplines here. So anyways, so now giving it all to you in all my classes, there probably will be more than 24. So that's not going to be the case this year, I hope, but it wouldn't surprise me if at this point there is less than 24 applied just because of past performance. Anyways, so I kept thinking, oh, I want to tell you guys, and then last week you had the test, so I go, well, I don't want to bother you during the test. I got next week. And then Monday I forgot, and then I was like, oh no, I got to do it today because it's due on Friday. All right, so like I said, grab one of those, and I got a big stack, so whatever the extras are, I'll pick those up at the end of class, but I want to pass those out to my class tomorrow too, so we can get a lot of people applying in there. All right, so back to 26 here. Oh, and I think I mentioned this, but I'd encourage you to go through and look at all those other ones. There's a lot in there, and not. But I think in this class, almost everybody would fit that one, whereas some of the other ones are very narrow, in scope, and so you may not fit it. It may be electrical engineering and your mechanical engineering, or it may be physics and your psychology. Well, you wouldn't be psychology if you're here, but you know what I mean. So or maybe the GPA. Sometimes the GPA is a little bit higher. It's a 3.5 and you only have a 3.4. Oh, and I meant to look. I think there is a GPA minimum though, so that can make it a little high. Yeah. So you got to have 3.0. So it's not unreasonably high, but it is still pretty high. So. Yeah.
I found weird that it said that they only gave the choice for computer network engineering and electronics, and no just regular engineering.
I know, and I've asked them about it over the years, and they said no, engineering's good too. So maybe I should call them again just to make sure that that's clear. But I think that was another reason why so many people weren't applying. If you read it real carefully, it doesn't just generally say engineering. But
so you review the scholarship?
Let me. I have in the past. I don't know if I will be asked to this time. It's kind of these mixed blessing things. It's like, hey, if you do, it's really kind of fun going through application because they submit a personal letter, and everybody's got their own unique story. I was raised in poverty, blah 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 blah, or I'm I was an orphan, or I spent time in jail, and so everyone's got their own background. So it's always really neat to see what challenges people are overcoming here, but it's a lot of work. So I'm kind of hoping they don't ask me, to be honest. It takes a lot of work and a lot of time. Okay, so now back to this problem. All right, so here is the problem here. I'll go back and read it again here. It says a 5 kilogram block is placed on a frictionless horizontal table and is connected to a string that passes over a pulley and then is fastened to a 9 kilogram object as shown in the diagram. Find the acceleration of the two objects and find the tension in the string. Okay, so there's our question. What is the acceleration? What is the tension? Okay, fair enough? Step one, we good? Good physical picture of what's going on, two blocks. Now they're connected.
Wait.
Maybe we should study that for a moment. Yeah.
Is there any friction?
No, frictionless. It says it's frictionless. Okay, so there's no friction up here. Okay, good. Maybe we should think about this. What might happen? What do you think would happen if you just kind of just let that go and stood back? Would it move?
Yes.
Yeah? Would this go down? And as it goes down, anything else?
It would accelerate because there's no friction.
Would it pull this one? How are these two going to be related? Oh, so they're going to, in other words, this goes down a meter, this goes over a meter? Right? So if this had a certain speed, say 7, what would this one have? 7. If this had an acceleration, say a 4, what would this one have? 4, right? I mean, there's a direct one-to-one correlation, right? Okay. So if I call this acceleration number 2 and acceleration number 1, I can say acceleration number 1 equals acceleration number 2. You good with that? All right. I would agree with that. But that's important to see here because that won't be the case in the next problem. We're going to have to analyze it real carefully. Yeah.
You say it's frictionless, right?
Yeah.
Then we're going to keep going.
Well, okay, so it's going to go and crash and fall. But during this part, I think is what they're asking. What's the acceleration? All right. Now, would the acceleration be 9.8? I mean, would this go down at 9.8? I mean, I'm letting it go. Yeah, see, it's not a free fall, is it? I get 9.8 on a free fall. How come it's not a free fall? Yeah, I've got tension in here, right? This is keeping it from falling. Now, if I came along and cut it, what would happen there? Yeah, that'd free fall 9.8. And then what that would be? That'd be 0 acceleration, and it would, right? Okay. So it's not 9.8. So all I really know is it is going to be moving, and they're going to have the same displacement, the same velocity, and the same accelerations. But I know it won't be 9.8. It's going to be something less than 9.8. But I don't know what it is. I just know that A1 equals A2. And that's that first step. Good physical picture of what's going on here. Yeah.
We're neglecting the elasticity in the rope too.
Oh, yeah. So the
moves a little bit, then it's going to maybe store energy.
Yeah. So you might say overly simplified since, you know, we're learning one step at a time. So our rope doesn't stretch, doesn't have an elasticity to it. And for that matter, the rope doesn't have any mass either. So I'm not worried about the mass of the rope. And for that matter, the pulley doesn't have any friction or any mass either. Now all those will begin to change as the semester goes along. Especially in chapter 11, our pulley, we will add mass to it, we will add size, we will add friction, and it'll get much harder. But until we get there, this is where we'll start here. So one step at a time here. But that's that first step. Good physical picture of what's going on. Because then step 2 is draw the free body diagram. Or in this case, I picked it because it's free body diagrams, plural, right? And so I have a free body diagram number 1 for object number 1. But I will also have, and maybe I should give myself more room and do object 1 on that middle board and object 2 over here on the far right board. But I would have free body diagram number 2 here. All right, so let's come over here to number 1. So number 1 means draw the object. So there's the object, 5 kilograms. Nothing else, no pulleys, no second block, no table, just the forces. All right, so what forces are on this?
Tension.
Okay, there is the weight. That is M1G, good. I heard another one, normal. Normal is up, N. I won't bother to call it N1 because the other one doesn't have a normal. Okay, so I'll just call that an N. Any others? Yeah, the rope itself, right? The rope is pulling it that way. Anything else?
No friction.
And there's no friction, so if there was, I'd put that one in there. Okay, good. Yeah, that's it, right? Look at what's touching it, table and rope, and the force of gravity. Okay? And the table could have had that fourth one, friction, if it was a friction problem. But all right, so there's the free body diagram for number 1. All right, let me come over here. Object number 2. What's the free body diagram look like? Okay, so the cord or the cable's pulling it up. And yeah, M to G pulling it down. Anything else? No? Again, only one thing touching it. That cable, that rope. And then force of gravity. All right, so there's my 2 forces here, my 2 forces there. All right, so I think I got step 2. Free body diagrams. Okay, so good physical picture of what's going on. Free body diagrams. Next, write out the equations. Which, of course, writing out the equations mean I need a coordinate system. Now, I don't see any reason by doing anything but the traditional here. You good with that? I'll just put the traditional one here. Maybe I'll put it over here to the side so you kind of know what the coordinate system is. But as I write out the equations, I would say, okay, the sum of the forces in the x direction equal mass times the acceleration in the x direction. And maybe I should have at least asked, which way does this one accelerate? Yeah, it's horizontal, and my clue to you in the last problem was set it up so your axis is along that acceleration, which our traditional one does have a horizontal axis, so there's no point in changing it. All right, so there's the forces in the x direction, and then the second equation would be the forces in the y direction. All right, well, let me start here. Forces in the x direction. What forces are in the x direction? Yeah, just T, right? So there's T. What does that equal? Well, that's all the forces, so it must equal the mass of this object, 5, times. All right, there it is, acceleration number 1, right? Which maybe I don't even need to put an acceleration 1 and 2 anymore, because we said they were equal. So it'll be okay if I drop the 1 here? Just put an A, because that's going to be the acceleration. Just all right. Now in this case, I can't solve anything because I've got 2 unknowns. I've got tension and acceleration, and I don't know what those are. Okay. Hopefully, some of the other pieces up here will allow me to have another equation to work that out. How about the vertical direction? What would that look like? Okay, normal force minus m1g equals, what does that one equal? Okay, so it equals the acceleration in the y direction. What is that? So it's 5 times what? Is it 9.8? It's 0. Is it accelerating? No, right? If it was free fall, would it have an acceleration downward? 9.8? Yes, all right. So it's easy to get those confused, but this is not saying mg. That's what this one is for. Okay? This one is saying that the combination of these 2 forces result in this much acceleration. That's Newton's second law. Add up all the forces to see what acceleration you get. Had you only had this, then your acceleration would have come out to be 9.8. But we don't. We have an upward together with its weight, resulting in a balance, if you will. Now this one, once I solve it, says the normal force is mg. The m is the 5. The g is the 9.8. That comes out to be 49 newtons. Now I don't know if that's even needed, but nonetheless, it's a good educational step there. I added up all the forces, I solved the equation. This tells me the normal force. Now, they didn't ask me to find the normal force, so I'm not sure it was, a wise use of my time in sense of solving a problem, but nonetheless, I could solve it. And if there had been friction involved, the friction would have involved the normal force. So I wanted to make sure for your education, I went through and I did it. I got the normal force. Okay? But that doesn't really help me with what I'm after, which is the tension and the acceleration. So although it's true, and in this case, notice the normal force does equal the weight. As I said, sometimes it does and sometimes it doesn't. Certainly never assume that it does. But this time it does. Here, I have no more information. So maybe I'll get it over here. So let's do the same thing over here. Here's the second object. Shall we set up a coordinate system? Do you want to stick to the traditional one? Okay, you guys kind of hopefully see the dilemma here. That sticking to the traditional one is kind of nice, but it also leads to, I think, some challenges here that you got to make sure you recognize. First of all, if I stick to the traditional one and call this X and call this Y, which way does this one move? Y. So which way is the acceleration? Y. Which way was the acceleration over here? X. So I'm going to have to correlate X with Y. Now I don't think that's so hard to do, except you better recognize it. Okay? And that's fine. So shall we leave it that way and then just remember it? Okay. But I certainly could have turned it so that the X was in that way. So the X here matched an X here. And I don't know if that would be better for you or not. But I'll leave it the way it is, since that's what I heard most of you suggesting. Okay, fine. And I will write out the equation. What is the sum of the forces in the X direction? What is the sum of the forces in the Y direction? Well, I'll start with the boring one, but nonetheless true. What are the forces in the X direction? 0. How much acceleration do I get in the X direction? 0. Okay, yeah, it worked. 0 equals 0. Perfect. Okay, and so it does work, just like this one worked, but doesn't really help me with this. So the X direction is not going to get me anywhere. How about the Y direction, though? Should we do that one? Okay, what's the sum of the forces in the Y direction? T minus M2G equals 0? How come it's not 0? Yeah, it does have an acceleration that way. Okay, so it would be what? 9, I heard? Kilograms times? A1, A2?
It's the same thing as A.
Just A? Doesn't matter? All right, good. There's one little problem in here. Do you see it? Because I can do all the math right from here on out. But if I miss this little problem, it's still going to be wrong. I got the wrong equation, and therefore the wrong answer. Yeah?
Why is it T minus mg instead of mg minus T?
That-
Because isn't it going down? I just don't understand why it was not reversed.
Okay, you're actually on the issue of the problem. I mean, what's wrong here? I mean, I put it as T minus mg. Why? Yeah, because you said right here T is positive. So there's the positive force. Mg is negative, right? So this looks kind of right until I realize I set it equal to A. But A's down, right? A's got to correspond with this A. So doesn't this have to be then a negative? Or, quite honestly, I would prefer to call down positive. And then I don't have to think too much about the signs and say, look, when this one moves positive X, this one moves positive Y. And if I do that, I would get an equation that has the mg positive, the tension negative, and the acceleration positive. And I think that's where you were headed. Which way does it go? Well, which way do these go depends on how you pick your coordinate system. Then about the sign of the A depends on how that acceleration matches that coordinate system. And so that was a big reason I picked this problem, because it's got the two objects and you want to compare them.
Wait, can you say that again?
So whether I put a plus or a minus in front of the forces depends on my coordinate system, right? So here I put positive t because I was calling up positive and down negative. That makes sense. Now if I reverse the direction of my coordinate system, then I'm calling down positive, so I put a positive here and then a negative there. So either one of these is correct, sure. But what do I do over here? And if I call this A and want to correspond this A with this one, I realize over here it's positive. But in this coordinate system, I'm calling it negative, so I need to put a negative there. Whereas in this coordinate system, I'm calling down positive. So I kind of like this coordinate system because it has a positive A when this one has a positive A. And I don't have to think about putting a negative sign in front of it. But I think you can see that equation is identical to that equation. So you could do it either way. You could do it this way, you could do it that way. Just make sure you catch it. Don't forget to put a negative there. I would suggest this, is what I would suggest. I would suggest if you have two objects moving like this, if this one moves in a positive direction, set it up so that this one moves in a positive direction. And so my positive A goes with a positive A, and I don't have to throw in a negative A here to match a positive A over there. That would be my suggestion. But I do want you to see that there's no right or wrong way. There's no one unique way. There are many wrong ways, but no unique right way of doing it, as long as we're consistent here. And of course, that's what I'd be looking for as I was grading your test. It's like, oh, I wouldn't have done it that way, but all right, let's see how they do it. All right. And as long as they're logically sound, I can't disagree with it. Say, okay, maybe that was a harder way or a long way, but it's logically sound and got to give you full credit. Yeah.
So you're just using positive y going down for this number 2, but
Yeah.
number 1.
Yeah. So that's why this gets a plus sign, because it's pulling down. Down is positive. This one is pulling up. So up is negative. And it is moving down. So down is positive. So I would, like I said, I would prefer to think about it in terms of that equation. But your choice. And that's one I wanted to point it out. But now, can you see I can answer the question? 2 equations, 2 unknowns. And that's what this one is. Set up 2 equations, set up 2 unknowns, and solve. So as I go to solve it, why don't I just do a substitution? This would be M2, so this would be 9 times 9.8 minus the tension, which would be 5A, equals the, M2, which is 9, acceleration. Move this over to here. That's a 14A equals, well, if that was 9 times 10, that would be 90. Thank you. 88.2? 88.2. So A would be 88.2 divided by 14. And then once I get A, I can get the tension would be 5 times the A. 6?
6.3.
Yeah.
6.3?
And that
31.5? Okay, so there would be the math as you work out solving 2 equations and 2 unknowns. All right. How about 32? Should we try a little harder one here? 32 is very much like this. Except their picture looks much harder. They've got this table and a pulley again. They've got this mass hanging, number 2, just like before. But this time it comes around, and instead of connecting directly to block number 1, it connects to a second pulley that can move with it, and a second string that is tied around that pulley and back to the wall.
Wait, how does that pulley connect to?
Yeah, let me read it and then we should talk about this, because again, you can't go anywhere until you a good physical understanding of what is connected here. And this is going to take some time to get this one here. But it says, an object of mass 1 on a frictionless horizontal table is connected to an object of mass 2 through a very light pulley, P1, and another fixed light pulley, P2, as shown in the figure. Then the questions go on and say, what is the relationship between the acceleration of block 1 and block 2? What is the tension in each of the 2 strings? What is the acceleration of A1 and A2 in terms of M1, M2, and G? All right. But let's go through these 4 steps. We'll start with a good physical picture. Do you kind of see what's going on here? Let me just kind of run through this. I've got a block with a string tied over a pulley. That's probably the easiest part, right? Fair enough? But then I've got another pulley here. And so this wheel can go around. In other words, when this gets pulled, let's say I come over with my hand and I pull it down. What's going to happen? It's going to pull this pulley over to here. So I will draw the pulley over to here when this goes down. And as that pulley comes over, what happens to this block? Right, as it pulls, this block's going to have to come over because now this rope's got to extend out to here and come back. Fair enough? And so I guess the first part of this picture is, does block 1 move? And which way does it move? Well, if the weight goes down, if number 2 goes down, number 1 goes to the right. Fair enough? Now here's the first question. If this goes down some distance, or some velocity, or some acceleration, so A2, V2, R2, how does this one move? A1, V1, R1. Do they have the same acceleration? And if the answer to you is no, then what is the relationship? And this is where chapter 2 comes back into play. Maybe I'll start something simpler. What about the distance R2 compared to the distance R1? In other words, let's go through a little mental exercise. If you pull this down 1 meter, how far does this pulley come over? 1 meter. You already answered that this block moves over, but how far? Does it move over 1 meter? Half a meter? 2 meters? And I claim it's 2 meters. And maybe you can see it in the extra string. If you pull this 1 meter over, doesn't this rope have to go out a meter further? And then a meter back? If this cord was elastic, let's say this was held into place with bolts and the cord was elastic, and you pull on this and you pull it forward, doesn't the cord have to stretch 2 extra meters? Now, if the cord is not elastic and it can't stretch, where's it going to get that 2 extra meters? By having this move 2 meters closer. So this R1 is twice R2. If R2 goes down 1 meter, this goes over 2 meters. That's the physical connection. There's no equation I can point out in your book, and nothing we can derive to figure out what is the mathematical. You gotta look at the picture and the pulleys and the connection between them. This is a 2-to-1 ratio. So most of you saw a 2-to-1 ratio, so that was good that you didn't say it was the same distance. Then it gets kind of hard to say, is it 2-to-1 or 1-to-2? You know, is it half a meter or is it 2 meters? But if you got that much figured out, then you can kick into your knowledge of chapter 2. How do you get velocity? Can I just take the derivative with respect to time? And if you take the derivative with respect to time, don't you get this? And what would you call dr2 dt? Velocity of block number 2. And what would you call dr1? Velocity of number 1. And so, because of the 2-to-1 ratio of their position, you're going to get a 2-to-1 ratio of their velocity. Sure, not a surprise. And you can then get the velocity. So, if this one was going down at 5 meters per second, this one would be going over at 10 meters per second. And could we do that again with the acceleration? Take the derivative yet again, and you are going to get that. This would be twice the acceleration of number 2 is equal to the acceleration of number 1. And that was this first part A. What is the relation of their accelerations? It's 2-to-1 ratio. If their position is a 2-to-1 ratio, once you have position, you get velocity acceleration, right? You only need to know one of them, and you can get the others. Okay? And that's what this one and the next one are showing. You know the positions, you can get their accelerations. Okay? So that's the first part of this. But the problem asks for a lot more than that. The first one just says, you know, what is their relationship of their accelerations? But the problem goes on to find out and ask, what is the equation for the accelerations in terms of their masses, and what is the equation for the tensions in terms of their masses? Okay? So, I guess we've done step 1. Good physical picture of what's going on? Let's go to free body diagram. So the free body diagram of number 1 looks like what? Well, here's M1 by itself sitting on the table. What forces are on it? Okay, so we've got its weight pulling it down. So there's an M1G. Anything else? Got normal force pushing it up. Anything else? I've got the tension, but now wait a minute, don't I have 2 different strings? All right, so tension of which one? Yeah, this one here. So maybe I better call that tension number 1 so that I don't confuse it with the string on number 2, which I'll call number 2. So this would be T number 1. So there's my free body diagram for number 1. What is my free body diagram for number 2? M2. Well, I guess it too is pulled down by its weight and being lifted up by tension, number 2. Fair enough? All right. So, have we done step 2? Free body diagrams? Step 3, write out the equations. All right. So that means have a coordinate system. Shall we just do the traditional one here? All right. It does move along the x-axis, so seems like a good approach here. Let me do the conventional, standard, and write out these forces. So if I take, let's get the sum of the forces in the x direction, that has to equal to m1a. What are the forces in the x direction? Yeah, it's just tension 1 equals to m1a1. All right, well, say there's equation number 1. How about the forces in the y direction? Well, I guess I got a normal force. I got an m1g. What is the acceleration in the y direction? 0. And so normal force is m1g. Doesn't really help me with acceleration or tension, so that I probably don't need that one. But nonetheless, it's true. So I won't put a box around it unless I think I might need it, but I don't think I'm going to need it. But that's one relationship. Okay. How about we jump over to object number 2? Let's write out the equations there. What coordinate system do you want to use?
On the side.
Can we call down positive now? Kind of like we did last time? All right, so let me go this and call down positive. Because that way, the acceleration of this one, positive, relates to a positive acceleration this way. Now if I do that and I say, well, let's look at the forces in the y direction, is it be okay if I ignore the forces in the x direction? There aren't any? All right, so let me just skip over that one in the interest of time and go to the y direction. In the y direction, I've got an m2g. I've got a minus t2. That has to equal to m2a2. And so there is yet another equation relating tension, and this is number 2, and this is A2. So I've got an equation here and an equation here. But they're asking for 4 things, aren't they? What's the acceleration of 1, acceleration of 2, tension of 1, and tension of 2? How many equations do I need? 4, don't I? Don't I need 4 equations to solve for 4 unknowns? How many do I have? There's 1. There's 2. Oh, good. There's 3. And this is one of those good problems that, you know, I seem to spend hours trying to solve this. They're missing a 4th equation. So, you know, step back and, you know, 4 equations to solve for 4 unknowns. You're not done here. Do all the math you want. You're just spinning your wheels. I need another relationship. What am I missing? What about tension?
Relationship between.
Yeah, what's the relationship between T1 and T2? Can I get that anywhere? Are they equal? No, I have no reason to believe they're equal.
T1 twice T2.
Okay, I hear a lot of 2-to-1 ratios, and I'm not saying you're wrong, but why would you say that? So why don't we do another free body diagram where the two chords are tied together and we'll have a T1 and a T2 in that equation, right? Can we get the relationship where they're tied together? Wouldn't that make sense? That's what I wanted you to see. So I need another free body diagram. So free body diagram number 3. Okay? And in this case, it's going to be that pulley, that movable pulley. And so as I draw the pulley, it looks like that one wraps around, T1 pulling this way and T1 pulling back again, and then it goes this way, which is T2. And if I call that the x direction and say, well, let's look at the sum of the forces in the x direction, It looks like I've got a T2 pulling it forward and 2 T1s pulling it backwards. That has to equal mass times acceleration. And what is the mass? They said it was a very low massless object, so I can put a 0. So that's a 0. Not because the acceleration is 0. This one has an acceleration, right? But its mass is 0, so maybe I'll put 0 mass acceleration of number 1. But either way, it's still a 0. And then, as somebody pointed out, there must be a 2-to-1 ratio. Yay! Okay, there we go. So now I have 4 equations and 4 unknowns. Now I can finally get to step 4, math. Okay? Solve the math. But again, hopefully you're getting the idea. You're never going to think of a physics class as a math class. It's just kind of the last step. I mean, you got to write it down, but... Yeah.
Wait, read the problem again? Does it just say low mass? Or
oh, shall I read it? Yeah, no, it says negligible or something like that. It says a very light pulley. Yeah, so it's a code word there is don't worry about the mass. In the equation, set it to 0 and take the limit as the m goes to 0 if you want to be a little more formal with the calculus.
If the masses were different, would the tensions then not be related that way?
No, the masses, I have no idea what the mass relationship is between the two blocks. And the tensions are 2-to-1 only because the pulley is massless.
I would say,
So,
mass 2 has to be bigger if it's moving.
no.
Not necessarily, because there's a 2-to-1,
Yeah.
there's a mechanical advantage here, yeah.
So it doesn't matter what the masses are, it's always 2.
And for that matter, you're not lifting it up. So any weight would pull it sideways. It just matters how quickly it's going to go sideways, because there's nothing stopping it from going sideways. Anything pulls, take it sideways. I'm sorry, go ahead.
So, well, it seems like to me that if the masses were different, the tensions would not be related this way, or would they?
Oh, they would. They still would be. It still would be the same free body diagram. Okay? And maybe this is a good example to illustrate. Is there a lot of other things going on with the masses? Yes, but don't make it hard. Just draw the free body diagram. All I'm interested in is the forces on this object. Is there some other mass over here with different mass? Sure. Is there some mass over here? Sure. But what are the forces on this object? That's why we do a free body diagram. We change what could have been something hard. Very simple. It's a very simple principle. We just have to apply it 1, 2, 3 times.
I guess I'm confused on like where the tension is like coming from. Why are there 2 T1s?
Yeah, okay, and again, this is back to the physical picture, a little bit, you know, connecting here. But if this is really Newton's third law, if this part of the rope is pulling on this way, then the other end is pulling equal and opposite. Okay? And so we have this cord, but it's, if I can do a better job here. If it didn't wrap, if it was just tied right here, I think you would see, okay, the rope has to have this net force of 0 on it. And so one end of it is pulling one way, so the other end is being pulled the other way. When you wrap it around, then it's kind of like a second cord, a second rope, but the tension is all the way through this. So is it pulling right there? Yeah. And is it pulling right there? Yes. If this was just one rope, and you pulled on it, would this point on the rope be pulling you? Yeah. But now would this point on the rope be pulling that other point on the rope? Yeah. So there's tension. That's why we use the word tension. There's a force everywhere in that piece of the rope. So this piece of the rope, as it wraps around, this part is pulling that way, and this part is pulling that way. And this is how you get what we call mechanical advantages with pulleys. It's the same rope, but when you wrap it around like this, then that same tension is pulling twice. No, it's because of the rope. I mean, anything that wrapped around like this would then, this edge of the rope is pulling that way, this edge of the rope is pulling that way. The fact that the pulley can spin real easy allows me to say that the tension is the same. If this was just wrapped around a metal bar, then this end would pull, but there probably would be some friction here, so this end would also pull, but probably at a slightly different value. And I would have two different tensions on those different halves of the rope. Well, maybe in the interest of time, I better leave this one alone, or should I try? Well, maybe I'll try to solve it real quick. Okay, so here was the problem, right? It was a big problem. It was 4 equations, 4 unknowns. We want to get, say, acceleration here. So maybe the thing to do is to do a substitution and put T1 equals an M1, and in place of A1, I will put 2A2. How's that? So I will substitute that equation into there. Now, once I do that, then I will substitute this equation in for A2. So this would be an M2G minus T2 over M2. So there's a substitution of this one, which is an A2, right? And then finally, T2 can be substituted into there. M12 equals M2G M2. And then in place of T2, I will put minus T1. And now I have an equation that only has a T1 in it. And I can solve for T1, right? I did my 3 substitutions here. So maybe to simplify this a little bit, I will put this over to here. So that's M2T1. I will multiply this out. That is a 2M1 M2G. I will multiply this out. That's a 4M1 T1. I will move this to the other side of the equation. There's the M2 plus the 4M1, M1, and factor out the T1. Then finally, I will get the equation that they want. What is the tension in number 1? 2M1 M2G over M2 plus 4M1. There we go. Wasn't that easy? So yes, there's a lot of steps here in terms of the mathematics. And I don't think you would have guessed that from the beginning, what the tension in number 1 is. But hopefully you see how it starts with a very simple idea. Draw the forces, set up the equation, solve the equation. That's it. It's just 3 objects, 4 equations, solve, you know. And so the work builds on you. If you wanted to go to T2 then, T2 is twice that one. So you just got to double this. And you get T2. If you wanted to get acceleration, number 1, that would be the T1 divided by an M1. So if I take my T1 and divide it by an M1, the M1 would go away, and I'd get that. And if I wanted A2, well, A2 is half of A1. So I would just divide by a 2. There we go. And so I've answered the question. What is the equation for T1, T2, A1, and A2 in terms of the masses? Right? And so obviously the problems started easy and got to have a little harder as we have moved along through this hour here together. What number was that? 32? I guess I'm going to have to make a judgment call. What might be a nicer one? Let's try 42. And I guess I just can do, you know, what I can in the short time we have. But I'm hoping you're also getting to the point of, if I dare say, being bored, in the sense that, oh yeah, all he did was set up the free body diagram, write out the equations, and solve it. I could do that. Good. That's exactly the point here. 42 is a nice one. It's kind of this same setup with the blocks, but this time we'll put friction on it, and it's got 3 blocks instead of 2 blocks here. But 42 says 3 objects are connected on the table as shown in the figure. The rough table has a coefficient of kinetic friction of 0.35. The objects have a mass of 4 kilograms, 1 kilogram, and 2 kilograms as shown in the diagram, and the pulleys are all frictionless. So here is the object on the table, 1 kilogram. It is then tied to a cord or a rope that goes across a pulley and then down to a 4 kilogram object. There is a second cable or rope connected to another pulley and another hanging weight that is 2 kilograms. And so that's kind of our picture here. The question is this: determine the acceleration of each block and the direction that they move, and find the tension in each of the 2 cords. Okay, so we're back to those same basic questions, acceleration and tension. And you can see why. I mean, that's what forces and acceleration. That's what this whole chapter is all about here. Well, which way is it going to move? Why don't we start there? And that's part of, do you see the physical picture that's going to go on here? I mean, maybe you could say, well, what if this block wasn't here? What would happen? Yeah, you would have 2 hanging weights. This one would be pulled down with more than that one, and you would have something going like that, right? So this one would go up, down, and this one would go up, right? You throw this in the middle. Let's say throw it in the middle without friction. Does that change anything? Without friction, it doesn't add any more forces, so this one is still going to be pulled down more than this one is pulled down. So this one goes down, and this one goes up, and then this one slides to the left, right? Now, what it does do is add more mass to the system, so that would probably have a lower acceleration, but still would go in that same direction. Now, if you throw in the last step where this one has some friction in it, what's that going to do? Yeah, it's still just going to slow it down more here, right? But it's going to still get pulled this way, and then that's why we have friction, opposite to the direction it's pulled. So, okay, so I think we've answered what's going to happen here and got a good physical picture. What's going to happen is, because of the gravity, this one gets pulled down. Now, I will call this tension number 1 in this first cord, because then this one pulling it up is T2, and then of course we've got a T2 there. And so that's part of our problem. What is T1 and T2? But I've got 3 objects. So I'll probably start here with, well, maybe I'll pause and say, I don't want to go too fast, but you got a good physical picture of what's going on? These weights that are hanging and now going to move. So then if I draw my free body diagrams, I will have free body diagram of number 1, calling this one number 1. I can have free body diagram of number 2, calling this one number 2. And then I would have free body diagram of number 3. Free body diagram number 3. Okay? But that's the point of the chapter. Draw those 3 body diagrams and write out the equations and solve it. All right, so we got a good physical picture. Number 1, I guess, would look like this. It's 4 kilograms, so it's going to be pulled down with 4 times 9.8, right? There's our mg. And it's being pulled up with a tension of T1. And hopefully that tension is less than its weight. That's why it goes down and not up. Okay? So that's kind of what I would expect from that first one. Second one is the more interesting one and why I picked the problem. What forces are here on this one? Good. So there's the T1 here, T2 here. Anything else? Okay, so good. There is a 1 times 9.8 for the weight. There is a normal force and friction. Right, so this one has some friction here. Okay, and friction opposite to the direction it's moving here. So we set that one up there. And so there's my friction. 3 then looks something like this, where I have a 2 times 9.8 pulling it down, and then a tension 2 pulling it up. And hopefully T2 is greater than the weight. That's why it goes up. So I expect this one to go up, and this one to go down, and this force is going that way, T1, to be greater than the combination of those two forces. Right? And so now I can write out the equation.
Can you calculate T2 just from the weight pulling it, or?
No.
No.
I mean, let me write out the equation. I mean, you know, I'm not going to assume anything, or maybe I'll get lucky and maybe I don't have to do all 3 objects. I don't know. But I know this, just Newton's second law. Write out the equation, see what you get. And if you get like 1 equation, 1 unknown, oh, you're going to be happy. You'll even be satisfied with 2 equations, 2 unknown. It's a 4 equations, 4 unknowns that you're going to kind of dread and go, oh, okay, I guess I got a lot of math in front of me. Okay? Okay, I need to pick a direction. In the short time we have together, is it okay if I just call this whole thing the x direction? Okay? So this goes up and over and down. All right? So when I say x direction, x direction, x direction. Okay? Goes up and over and down. So all my x's correspond. All my positives correspond. I won't have to do too much thinking from one picture to another. All right? So in this one, when I write out the sum of the forces in the x direction and set it equal to mass times acceleration in the x direction, calling down positive, I will go 4 times 9.8 minus T1 equals 4 times A. And that would be my first equation. Okay? And of course it has 2 unknowns in it, so by itself I can't solve it. Now I only put A. I didn't put A1 or A2 or A3. Why not? Yeah, and I think we talked about this a lot, that they're all going to have the same acceleration. If this goes down 1 meter, this goes over 1 meter, this goes up 1 meter. So this is not as complicated as the last problem in terms of their motion. It didn't have a wraparound pulley. We call a movable pulley there. Okay, so that would be equation 1. What about this one? Well, again, sum of the forces in the x direction have to equal mass times acceleration in the x direction. So looking at the x direction, I would have T1 pulling that way, T2 pulling in the negative direction, friction pulling in the negative, and I should stop. Kinetic or static friction? So if it's moving, it's going to be kinetic. So I'll put a little sub K down here, all right? So there is a kinetic friction as they slides across the rough table, as it said. And then I will have the mass of 1 times the acceleration. And maybe I'll put a box around that. That one's even worse. How many unknowns I got there? 1, 2, 3, 4. Whoa. All right, so I certainly can't solve that by itself. But these 2 are in there. So I have 2, it's not 2 plus 4, it's still a total of 4 unknowns, right? How many equations do I need? 4, unless I get luckier along the way, right? Yeah. They don't give us FK. They give us a coefficient. Okay, so maybe we'll head that. I was going to keep going on this direction, but somebody said, wait a minute, is that really an unknown? Isn't Fk equal to mu sub Kn? All right. So they don't directly give us Fk, but they do give us the coefficient. And was it 0.35, if I remember right? What number am I doing? 42? 0.350, yeah. And then times normal. All right, so if it makes you feel any better, I got another equation that has the Fk, unfortunately. Do I know n? Okay, I don't know it yet, but I can get it. So I don't know if you want to call it another unknown, but to me that's 5 unknowns, right? 1, 2, 3, 4, 5. But maybe that's good. How many equations I have so far? 1, 2, 3. So I need what? 2 more. Don't I have a y direction and another free body diagram? Yeah, all right. So we're going to get up with 5 equations, 5 unknowns. All right? And we're going to be able to solve this. Now, if it makes you feel any better, maybe you can do a substitution into there, and then it only looks like 4 unknowns. And then do a substitution here, and then it only looks like 3 unknowns. That might make you feel better. 3 unknowns, 3 equations. Okay? But I've got to add up the y direction also. And the y direction is going to give me the normal. So in the y direction, I have the normal pushing up and force of gravity pushing down. That has to equal to what? 0. Why 0? No acceleration in the y direction. So here, the normal force becomes 9.8. Now that's really helpful, right? That's what you guys were saying. That, hey, look, if you solve this one, you know n. Once you know n, you know f. Okay? So maybe I'll do that. I know n. Let me solve for f now. F is 0.35 times 9.8. So that is 3.43. And so if I put that into here, 3.43, you could say there's only 3 unknowns in this equation now, right? You could say there's an A, and a T1, and a T2. So I've used this equation and this equation to get that, but now I only have 3 unknowns. So I have that equation and that equation with 3 unknowns. So don't I still need another equation? Yeah, so I got to go over to here at some point. And so here I can go 2 times 9.8 minus T2 equals 2A. Oh, thank you. I messed up on my coordinate system. Positive up and negative down. All right, so 1 equation, 2 equation, 3 equations. So 3 equations, 3 unknowns. And solve. Right? Well, in the last half of minutes we have left, let me avoid solving the math here and then just throw one more out there. See if this makes sense to you. At least partial sense to you. If it does, you're in a good spot. Because remember, you know, the test on this one is still weeks away. And it does take a while for this to sink in. And it's not just 1 chapter long. Newton's second law here is 2 chapters long. But look at number 44 for just a quick second. I'll at least set up the free body diagram. We won't have time to write out the equations per se here. But at least let me do the physics part of it. 44 says this: take a block of mass 3 kilograms and push it against the wall at an angle phi. So here's the block. Here is a force, what they call P, probably P for push. So you're going to push on this block, but you're not pushing straight into the wall. You're pushing at some angle theta. So a block of 3 kilograms, although I'm not sure the mass is going to matter here, because it's not supposed to move. 3 kilograms is pushed against the wall by a force P that makes an angle of theta with the horizontal as shown in the figure. The coefficient of static friction is 0.25. Determine the possible values of P so the block doesn't move. Now, why would they even say possible values? I mean, what happens if you don't push very hard? It falls. So don't you have to have a minimum amount of pushing? Now, what if you push too hard? It goes up. That's why it said a range here. So what's the free body diagram look like? What forces are on this? Okay, obviously there's this force P at some angle theta, right? Any others? And one of the reasons I like this one is I got to put a normal force. Which way's normal? Perpendicular to the surface. It's horizontal this time, not vertical, right? What other forces are going on? Okay, gravity, mg, fair enough. And don't forget, what else? Friction, which way? All right, so if you push with a minimum amount, you are using the force of friction to help support it. If you push with a maximum amount, which way is the friction? Down, you're using the friction to stop you from pushing it up. That's how we can solve for the two cases. We can solve the case of what would be the minimum, what would be the maximum. Do I dare write them out real quick? Sum of the forces, x direction. Isn't that a p cosine theta from this one? Minus a normal from that one? Doesn't that have to equal 0? Sum of the forces in the y direction. What is that? Isn't that p sine theta pushing up? Force of friction pushing up, which is equal to coefficient times normal. Gravity pushing down, and we don't want that to accelerate. So there would be my equation. Over here, it would look very similar. I would have the x direction, so I would have p cosine theta minus n equals 0 there. But the forces in the y direction would be p sine theta minus mg minus the force of friction, which again is coefficient of friction times normal has to be 0. So the thing that changed is the plus sign to minus sign, but they're the same there. Well, I hope that was somewhat enlightening, because I know there's a lot of really complicated problems. But believe me, you have the information now to do it. And you standing there just reminds me, you want to make an announcement, right?
I do.
Okay, so two announcements.
So for those of you that aren't aware, Math Club is putting on a series of lectures this semester, and the one that's happening today, actually literally right now, 11 a.m.
Oh, 11, yeah, right now.
Yes, is of particular interest to people that are in this class, physicists and engineers. David Bennett has a master's degree in applied math. He just finished his research at Channel Islands, and he's talking about his research, which is in flame and candle dynamics. So that's going to be really cool. It's happening right now in the interdisciplinary building, IBC 109, right next to the math lab. So I hope we'll see as many of you as possible there. Also, we are organizing a group of people to go to the Pacific Coast Undergraduate Mathematics Conference, which is Saturday the 10th. So if you're interested in doing that, you have to register by Friday. If you just Google it, you can find it. It takes 2 minutes, super easy. And if you need more information, feel free to email me or find me on Facebook.